Okay, last theory video before we do the SPSS. And now we're going to extend our chi-square. We did the one-way chi-square in the previous demonstration. And now the two-way chi-square, where I've got two variables that I'm looking at. And in this case, I'm going to look at eye color by sex, male, female. And this is my sample. So these are my observed frequencies for brown, blue, and green-eyed people for males and females. The null hypothesis is proportions by eye color do not differ by sex. Alternate hypothesis, the proportions by eye color do differ by sex. So the hypothesis here is embedded actually in the data. So what I'm saying is, let's look at it from the perspective of eye color. Whatever the breakdown of eye color is overall, I'm going to use that as my null hypothesis, and it's going to be that, well, whatever the breakdown, if I ignore sex, and I have like 60 people here, if I ignore sex, I have a breakdown for brown, blue, and green-eyed people. The null hypothesis is that those proportions or percentages are the same for males and females. This is referred to as an interaction effect. And if I reject the null hypothesis, I'm saying that eye color interacts with sex, meaning that the breakdown by eye color differs between males and females. Now, the only tricky part with this one is the calculation of the expected values. It's pretty funky. We'll work. I'll give it an Excel example too. We'll do that in class. Same thing. It's the chi-square test. Formula stays the same for each of these boxes for brown-eyed males, blue-eyed males, green-eyed males, then brown female, blue female, green female. I have the observed, but for each of those, what they're referred to as cells. So each little box with a number in it is referred to as a cell. I will be able to calculate a chi-square because I'll have an observed and an expected. And what we'll do is, the only tricky part with this one is the calculation of the expected values. The formula in general to calculate an expected value for a given cell is whatever the frequency is for the column total, multiply it by the frequency for the row total, and divide it by n, the total number of people in the study. And you got to do it 6 times in this case, right? You got to do it for males by each of the eye colors for male. Then you got to go down to the females and do it by each eye color for female. So there's 6 calculations here. Okay. The first thing you need to do is you need to calculate your column totals and your row totals, right? So FC is the frequency for the column, and that would be the brown-eyed people. And the frequency for the brown-eyed people is the 5 males plus the 10 females, which is 15. The frequency for the blue-eyeds is 20 males, 10 females, which is 30. And then the frequency for the green-eyed, the FC for the green-eyeds, is the 5 plus the 10 is 15. Now, if I ignored the person's sex, the breakdown by eye color is 25% of the sample has brown eyes, 50% has blue eyes, 25% has green eyes. And my null hypothesis is that those proportion breakdowns, 25% brown, 50% blue, 25% green, in the population, that's the breakdown. So the breakdown by eye color in the population is the 25% brown, 50% blue, 25% green, right? So that is, and what I want to do is, I want to apply those percentages, the 25, 50, 25, to the number of males that I have and the number of females I have. So I have 30 males and 30 females. So I want 50% of the males, my expected value for the males for brown eyes is 25% of 30, which is 7.5, and then 50% for blue-eyed males, expected value is 30 times by 0.5 is 15. And then for the green is 7.5. So the 7.5, 15, and 7.5 gives me an expected breakdown of 25%, 50%, 25%. So here, all right, if I run through those calculations for each of those cells, that's what it looks like, right? So yeah, so if I take, you have to walk through those calculations. You got to do it for each cell. So for each cell, you take the expected frequency, multiply it by the row frequency, and then divide by 60. So it's 7.5, 15, 7.5, right? I got 30 males. I want 25% brown, 50% blue, 25% green. I got 30 females. 25% of the 30 are brown, 7.5. 50% are blue, and 25% are green, right? So that's where the 7.5, 15, and 7.5 come from. It is 25, 50, and 25% broken down by the 30 males and the 30 females. Those are my expected values. Then it's just simple calculation of the observed minus the expected squared divided by the expected. So here are each of my calculations. I got to do it 6 times. So male brown, male blue, male green, female brown, female blue, female green. I do that calculation, and then I add it up, add the values that I get here, and the total is 6.667. So my chi-square observed is 6.67. The degrees of freedom in this case is the number of rows minus 1 times by the number of columns minus 1. So I have 2 rows, male, female, so 2 minus 1 is 1. I have 3 columns, the brown, blue, and green. 3 minus 1 is 2. 1 multiplied by 2 is 2. So my degrees of freedom are 2. My degrees of freedom are 2. My critical value, which I have on the next table, looking it up once again, 2 degrees of freedom with for alpha equal to 0.05. So I want the cutoff for the top 5%. That gives me a chi-square critical of 5.991. So my chi-square observed of 6.67 is greater than 5.991. Therefore, I reject the null hypothesis and conclude if the null hypothesis were true, then the likelihood of me getting the sample that I did is fairly unlikely. And I would conclude in APA style, the results of the study revealed that the breakdown of people by eye color was different for males when compared to females. Chi-square with 2 degrees of freedom, n equal to 60. Chi-square observed was equal to 6.67. P less than 0.05. So there's less than a 5% chance that I would get a chi-square observed of 6.67 if the null hypothesis were true. Practice. So what I would like you to do, and we'll take this up, I'll take these up in Excel, and I'll also take it up in SPSS. So we'll do the Excel and I'll do the SPSS for both the one-way chi-square and this chi-square.